I will be trying to get you the paper portion of the test back by Thursday, the coding portion I'm trying for Wednesday night, but a more realistic goal is probably going to be Friday afternoon when I have all the coding questions finally graded. So paper version hopefully Thursday, coding hopefully by Friday. And we are into the home stretch. Just so you know, I know, everyone's happy about that. The final is not comprehensive, so it just covers the material starting today, plus for the coding portion, it covers linked data structures. And today, we get into our second new programming topic, which is recursion. So at the outset of the semester, we said that there was a number of goals for the course. And one of those goals was to teach you to be better C++ programmers. And as part of that, there were two techniques or programming tools that you had not yet been introduced to in 102 and 130. One of them you've already seen, and that's pointers. The second technique is something called recursion. And that's what we'll be covering for the next 2 days. And then recursion is what is used to implement trees, which are the data structure that underlies sets and maps. So the last 4 weeks of the semester, we're essentially talking about the mechanics of how you implement the data structure that underlies trees, but also recursion is a powerful tool in its own right. It is essentially a flow of control tool like loops, like if-then-else statements. So it's another way to control the flow of execution in your program. And to motivate it, I'll give you a simple example from mathematics. And it's not perhaps the best example for implementing recursion, but it does show very nicely. It's the Fibonacci numbers. So how many have heard of the Fibonacci numbers? Okay, great. So I'm going to use one. There's kind of always some debate over whether they start at 1 or 2. I'm going to write mine starting at 0. So I'm going to say fib of 0 is 1, fib of 1 is 1. And then after that, we have that fib of, so this really should be fib. So fib of n is equal to fib of n minus 1 plus fib of n minus 2. This is called a recursive definition. So we're talking about recursion. So with recursion, a function is defined in terms of itself. Okay, and that's what's happening here, is Fibonacci number of n is equal to the n minus 1 Fibonacci number plus the n minus 2nd Fibonacci number. So if I asked you what f of fib of 2 is, it's equal to fib of 1 plus fib of 0. And those you already know, so you get 1 plus 1 is equal to 2. If I ask you what fib of 3 is, it's equal to fib of 2 plus fib of 1. I just told you, we just calculated fib of 2, so that's equal to 2 plus 1, or 3. Okay? So that's a recursive definition. And in general, we say that recursion is something where you break a problem into identical subtasks. So you break a problem into one or more identical but smaller subtasks. And then combine the results of the subtasks. So here we have broken the Fibonacci number into two smaller subtasks, Fibonacci n-1 and Fibonacci n-2, and we've recombined the results by adding them together. The way you implement recursion in C++ is with a recursive function. So you are allowed to have a function call itself. That is a perfectly fine thing to do. So for example, I could write a program. I'll call it fib.cpp, and so I'll have fib of n, and first of all I check to see if n is equal to either 0 or 1, because we call these the base cases. So this is where we know the result, so here we return 1, and otherwise we are going to return fib of n-1 plus fib of n-2. So there's your first recursive function. So it's calling itself smaller subtasks. Talk about that in a moment. So we'll have our thing, just we'll enter a number. So actually let's take it off of take it from there. And I'm just doing a quick and dirty program, so I am going to use the a to I function. I'm not going to be checking for any bad things. So fib of I equals fib of I. Okay? We good with that? So let's run that puppy. So let's make this smaller and run them side by side. So we run it on 0, it works. Run it on 1, I see I had a little bit of a formatting issue. Run it on 2, run it on 3. What should 4 be? 5, very good. So it's looking good. Still looking good. Still looking good. Uh-oh. Did you notice that? It was a little slower. Now you can go get coffee. So, there is an issue with recursion if you're not careful. And that is that what you're not seeing there was a bit of a explosion in the recursive calls. So, if you think about it, let's just look at fib of 5. It calls fib of 4 and fib of 3. Fib of 4 calls fib of 3 and fib of 2. Fib of 3 calls fib of 2 and fib of 1. You can see that there's a lot of branching going on here, right? And that's just for fib of 5. There turns out that if you're not careful with recursion, you can get an enormous number of recursive calls like this. I didn't even write out all the recursive calls because I was getting tired of doing so. They actually would end at the so-called base cases. So what was happening by the time I got up to 45 was that there were just so many of them, it was overwhelming the system, in effect. Okay, there was just too many calls that were going on. In fact, you can show that the running time, when I wrote it like that, was roughly 1.6 to the n power. And that's an exponential, which grows very rapidly. So it turns out that implementing Fibonacci as a recursive function isn't really the best way to go about it. It turns out there's a much faster linear algorithm where you simply iterate, well, I'll show it to you rather than. So here's the one from Dr. Planck that just uses a while loop. And he starts out by saying if n is less than or equal to 1, return 1. Otherwise, he's keeping his two Fibonacci numbers and he's building up toward the one that he wants, which is kind of what we were doing when I was doing it here. I was kind of building up to it, and you knew how to calculate it because you knew that Fib 4 was 2 and 3. You knew that Fib 5 was 4 and 3. So what he's doing is simply calculating always the next Fibonacci number as the sum of the previous two. Now his variable names may not be as clear as you would like. IM1, does anyone know what IM1 stands for? Pardon? Wasn't medium. It took me a little while to figure it out too. Intermediate. So he means it as intermediate 1 and intermediate 2. So he's just calculating the next Fibonacci number, and when he gets up to the nth one, he returns it. And if he's not yet there, then he sets his intermediate 2 to intermediate 1, and he sets his intermediate 1 to the new one that he just calculated. So he's just calculating the trailing 2, and he just keeps building up. And that's actually an order n algorithm, which is a lot more efficient. It's also less elegant, right? It's much, compare this one, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, about 11 lines. This one had 4. So recursion often leads to much more elegant specification problems, but if you're not careful, it can be a little inefficient. Now, I said it's like a control structure, and that's because you're calling a function, and it's at some point you want the execution to terminate. You don't want, just like you can get infinite loops, you could get infinite recursion. And you want to make sure that doesn't happen. So if you look back at my definition of recursion, you'll see that I said you break the problem into one or more identical but smaller subtasks. So the goal is to always break it into a smaller subtask. And eventually you want to get down to what we call the base cases, which are the cases we know the solution for. So with Fibonacci, you notice that first of all, the two cases were actually smaller. N was getting smaller with each successive call. And eventually, we did have our base cases with n equals 0 or n equals 1. And in those cases, when n got down to those two values, we simply returned 1. So with recursion, when we write a recursive function, we generally talk about the base cases and then the recursive case. So the base cases are inputs for which we know the answer. And what we're trying to do is make our tasks excessively smaller so eventually we reach the base case where we know the answer. Okay, so that's where we stop. So generally a recursive function, the general form of a recursive function is going to be like this. Okay, you'll have some, we'll call it just recursive, and some input n. So you say if n is one of the base cases, then return the known result. Okay, else, okay, state the problem in terms of one or more smaller subtasks and combine the results and return the combined results. Okay, so that's the general form of a recursive function. And the base cases, they're very important because if you forget the base cases, you'll get an infinite recursion just like you can get a infinite loop. So actually let me go back and I'm going to comment out my base cases. And when I comment out my base cases, what's going to happen is n's just going to keep getting bigger and bigger negative, right? So watch what happens. We'll do fib of 3. Whoops. Segfault. Sometimes you get what's called a stack overflow error. Sometimes you get what's called a segfault. So it'll look just like a pointer problem, but that can happen with a infinite recursion. So questions about that first? It's a rather simple example. Okay. So here is another example, and it's going to seem a little counterintuitive. That's okay, but it's at least a simple example. Suppose that I want to sum up the contents of an array. So I have an array, and I want to sum the contents of that array. Well, I'm sure you could all write a while loop or a for loop that steps through the array and sums the values. But there's another way that you could do it. Okay? You could break the array in half. And you could recursively sum each of the two halves. So you could sum this half, and you could sum that half. And then you could add the two back together. And you could treat the base case as the case where either the array has 0 elements or where it has 1 element. If it has 0 elements, we probably would return 0. If it has 1 element, we return that element. So it's kind of like the base case is if 0 elements, we'll say the result is 0. If 1 element, we return that element because that's the sum of 1 element. And then our recursive case is, let's say that we've been asked to sort an array. So let's say we have sum of some. Okay, we've been working with vectors, so we'll call it a vector. So we have a vector v. Let's say we want to sum it from the low subscript to the high subscript. So low might be, say, this might be low, this might be high. Okay, so then what we would do is we would sum each half. So we would sum V from low to low plus high divided by 2 plus sum of V from low plus high divided by 2 plus 1 up to high. So that's a recursive definition for sum. Now, not claiming this is the way you should do it, what I'm trying to show you is that you can often come up with a recursive definition of a task as well as one that is an iterative definition. So this one, again, I'm just summing the lower half, adding it to the sum of the upper half. So I'm just breaking it in two. And you might say this is unnatural. But let's say that it was a competition. I broke the class into two parts and I gave you an enormous quantity of numbers to sum up. And I said, whichever half of the class I'd really incentivize, you get, say, $1 million. Do you think you just tell one person to sum the numbers? Or which side do you think would win? The side that delegated the summing of the numbers? Let's say there was 10 people in your group. And would you really just have one person sum up all the numbers? Well, I bet my group of 10, if I delegate to 10 different people the summing and then add up the sums returned by those 10 people, I'm willing to put my money on that group. Now, you're right. You might have someone who's really good. But I'm guessing you would think about delegating, right? You probably would divide up the task of adding up all those numbers to all the people in the group. Okay? Well, that's recursion. You've just divided that task into, in this case, 10 smaller tasks, and you're recombining the results. So recursion isn't actually all that uncommon in the real world. We do it all the time in work settings where we divide tasks up and assign part of a task to one person and part of a task to another person, and then we combine the results together. In fact, recursion is what makes what's called parallel processing so efficient. Okay? If I add, say, 10 cores, most of your laptops now have multiple cores on them. If I just tried to do the summation of the vector on one core, the other cores are just sitting there twiddling their thumbs doing nothing. Wouldn't it be more efficient to actually assign part of this summing to one core, part of the summing to another core, and then sum the two results together? So this may seem on the face of it stupid to break it in half. But in fact, if I have multiple cores, that's the way to go. Because now the operating system can assign these subroutine calls to different cores, and the cores will operate in parallel, and you'll get your result faster than if you wrote a for loop. So recursion is actually a very powerful tool for accelerating the computation of tasks that can be parallelized with multiple cores. Okay? So while this wouldn't be something you would do with a single core, this is something you would consider doing with multiple cores if the operating system was smart enough to do it. Okay, so this was something that you might do to parallelize it. But let's now take something that might be a little harder to do if you didn't have recursion. So again, I'm going to give you an array. And I'm not going to make this 11. I'm going to change it to something else. I'll change it to 5. Let's say I want to sort this array. In 102, you learned a couple ways to do it, or should have. One was selection sort, one was insertion sort. But those were slow, you were told. There are faster ways to do it. Let me tell you two fast recursive ways to do it that you may not have been exposed to. The first way is an algorithm called quicksort. It is actually the workhorse sort algorithm that is used for most built-in sort functions, like in the scripting languages or in the standard template library. When you call sort, you're actually calling this algorithm called quicksort because it is the fastest known sorting algorithm. And it's amazingly simple, a really simple idea. At its core, you just look at the first element in the array, which is 5. And what you're going to do is you're going to rearrange the elements of the array so that every element less than 5 ends up on one side of the array, 5 ends up in the middle, and everything greater than 5 ends up in the upper half of the array. Okay, so you're just going to look at the elements in the array, and you are going to move them in such a way that you end up with this right here. Okay? So one way to do that is to simply start here and here. Actually, one way to do it is to move 5 off. So we can actually start here. And what we're going to do is we're going to keep searching until we find something greater than 5, which is 7, and something less than 5, which is 1, and we will swap them. So we're going to swap 1 and 7, because 7 should be on the right side and 1 should be on the left side, because 1 is less than 5 and 7 is greater than 5. Now we will move our two indices to point to the next elements, 6 and 11. Well, 6 needs to move because 6 is greater than 5. 6 needs to be moved to the upper half, but 11 should stay put because it's greater than 5. So we move this one to the left and we get 2. And now 2 is less than 5, so we need to swap 2 and 6 because 2 should be on the left side of the array, 6 should be in the upper half. So we'll swap 2 and 6. Okay? And again, we move our pointers to the next elements, which are 9 and 8. Now you can see that as we move this pointer, it's eventually going to cross the other pointer. So if we call this low and this high, eventually low moves past high because there's no number now left that is less than 5. You can also see that we have everything that is less than 5 in the lower half, everything greater than 5 in the upper half. The only thing we don't have is 5 in the middle, and we fix that problem by at the boundary, we move one of these two values here, we swap it with 5. Okay, so one of those two values is arbitrary. I'll swap. Whoops, I can't do that. It's not arbitrary. I have to swap the lower one. So I have to swap 2 and 5. So 2 goes here, and 5 goes here. Okay, so what I have done is I've changed my array, and now everything that is greater than 5 is in the upper half. Everything that is less than 5 is in the lower half, and 5 is in the middle. So what if I call quicksort now on each of the two halves. Okay, this may not be intuitively obvious to you, but if I call it on each of the two halves, it's going to do the same thing. It's going to keep getting smaller and smaller arrays with the lower values on the lower part, the greater values on the upper part, and eventually they're going to have sorted arrays. Okay, so let's keep doing that. Okay, so here for 2 and 1, we now have to sort 2 and 1. So the sort 1 is 2, and you can see that essentially low and high start at the same place. So we're going to end up swapping. Well, we'll end up not really swapping anything because they will end with 1 being on the left side and nothing, the empty set, being on the right side. So this symbol is meant to be the empty set. So I then swap 1 and 2. Okay. And I don't have to sort anything. The right side is empty, the empty set, so that's a base case. An empty array is sorted. And the left side is 1 element. Is that sorted? Is a 1 element array sorted? Yes. So our two cases for quicksort are an empty array, which is sorted, and a 1 element array, which is sorted. Okay, so that was easy. Let's do the harder one. Okay, so now we have to sort this one here, which is 8, 9, 6, 11, and 7. Okay, so this first element is always called the pivot. Okay, so what are the first two elements that will get swapped based on what I'm doing? If I start low here and high here, my pivot is 8. So I want everything less than 8 in the left half, everything greater than 8 in the upper half. So what gets swapped first? Pardon? 9 and 7. 9 is greater than 8, 7 is less than 8, so we need to interchange them. There's 7, there's 9. Okay, we move low and high. And very quickly, low is going to move past high because there's nothing less than 8 anymore. And now when we're done, we swap 6 and 8. Okay, so our next two that we would sort would be 6 and 7 and 11 and 9. And hopefully you see that they are slowly getting into sorted order. By moving everything lower to the left side, everything greater to the right side, we're slowly forcing everything into sorted order. Yes?
I still don't follow the case with just the 2 in it. Why do we start at the left-hand element again, right? Is that like the middle one? Or is that?
Yes, so we start for the case where we had 2, 1.
Yeah.
We start there.
Okay.
Okay, so now low and high are the same value.
Okay.
Okay? And we basically, when low is equal to high, we are going to, well, when low moves past high, we stop. Okay, so we're immediately going to move low 1 to the right because 1 is less than 2. That moves low off the end of the array. So it's immediately greater than high. And it turns out there's nothing to swap here. Okay, so I'm waving my hands a little because quicksort's a little bit difficult to do in the implementation, and I didn't do it off the top of my head. I thought of this example on the way in today, so I don't want to program it up in front of you. It's too easy to mess it up. But the general idea is you move everything less than the pivot to the lower half, everything greater than the pivot to the upper half, and then you put the pivot in the middle.
Everything when it moves off, and you know the trigger to swap the pivot in what's lower.
That's right. So at the end, generally, you're going to probably end up with high. If you're doing it really in the right way, should move so that it points to the first element that needs to be swapped. Okay, so the general kind of, if I were trying to write quicksort, the general idea is that the base case, there are two base cases, okay, 0 element array and 1 element array, they are already sorted. Okay, they are already sorted. So you just return them. You just return. The recursive case, okay, you choose a pivot element, and choosing the pivot element is often not as simple as choosing the first element, but we'll just say choose pivot as first array element. And you know that in this case, n is the size is greater than 1 in this case. So you know there must be a pivot element. And then rearrange vector so that all elements, and now if there's equal elements, you have to put them in one side or the other, it turns out. So I'll say so that all elements less than or equal to the pivot are in lower half of array, or lower half of vector, and all elements greater than the pivot are in upper half. Okay, then we move the pivot to the so-called middle of the vector. And finally, we call quicksort on lower and upper halves. So this is what's called an in-place sorting algorithm. So you actually don't return anything, because what you're doing, you're sorting the elements in the array so that when you return, the array is sorted. So you're actually working on the array itself. But this would be very hard to do with a while loop. Okay? This is very difficult. You would have to do some fancy maneuvering because you're piling up a lot of subcases here. Whereas with recursion, it's very handy. Okay? Because essentially, you work on one half and the other half is conveniently put off. Okay? And then you break that one half into smaller halves, and again, you work on one part at a time. Essentially, what you're doing with recursion is breaking a problem into trees, okay, or into subcases like this, and you're working on the subcases one subcase at a time while leaving the rest of this so-called tree for later work. So recursion is really just kind of building out what looks like an inverted tree. Okay? So I'm actually going to leave you right now. So we covered kind of two examples. We covered Fibonacci, which admittedly isn't very efficient if you do it with recursion. And then this quicksort, which actually is very efficient. It's the most efficient known sorting algorithm. Okay? So the question is, okay, if you can formulate this thing, so first of all, we've talked about how you formulate a recursive function. You make sure that you first have your base cases, then you make sure that your recursive case states the problem in terms of one or more smaller subtasks, and then somehow you return the combined result. So if you're trying to think of it recursively, that's how you do it. And I actually gave you a third example, which was this sum example, where you are summing the elements of an array. So you've seen three different examples of recursion. If this doesn't really appeal to you yet, don't worry about it. It's a tough concept for many students to wrap their minds around. It will get easier with time, but I'm not going to claim this is an easy concept. This is one of the hardest concepts, along with pointers, that you'll encounter in this course. Okay, so just if you feel frustrated, that's okay. It's not going to come naturally to everyone. But it is important. You will, with time, hopefully become more comfortable as you see more and more examples. Now, I will say in the notes, Dr. Planck goes over the towers of Hanoi. I'm not sure that I would look at this. If you're really up for a challenge, then it's certainly a cute, recursion is a very cute solution to the towers of Hanoi, but I do think it's a bit advanced at this point. So feel free to look at it, look at how he's doing it. I'm not going to cover his towers of Hanoi. You'll see the onion rings. The idea behind the towers of Hanoi, does he have the, nope, oh, come on, we got to have the, okay, so the towers of Hanoi, if you've never heard of it, is you have three spindles, and you have progressively smaller rings on the spindle. And what you want to do is move all the rings from the first spindle to the last spindle, subject to the requirement that in doing the move, you're allowed to put the rings on any spindle you want, but for every spindle, the pile has to always go from biggest to small. You can never put a bigger ring on top of a smaller ring as you move all the rings over to the right-hand side. So, for example, I can start by moving the small one over here, but the next move is forced. Okay? The reason the next move is forced is I cannot move the pink or orange ring, this ring right here. I can't move it next because if I did, I would have a bigger ring on top of a smaller ring. So what I actually have to do next, I don't have yellow. Let's see, so I have to use black. So I move it to here, and then I move the smallest ring to here. Next, I move this ring to right here. Okay, now I can move this black ring back on top. Okay, and then I can move the black ring back over here. When I do that, you can see that I now could move the red ring over to here, which means I could move this yellow ring back over to here, and I've accomplished part of my task because I now have two on the right-hand side. But I have to keep doing this in order to get all of the rings from the left-hand side to the right-hand side. And it turns out you can solve this very easily, not easily, but elegantly using recursion. Okay, So let's see if I can, I don't want to use ASCII art. And not there. Okay, we're not going to go over it. It's too difficult. I don't want to get into that today. But at any rate, suffice it to say that if you are interested, you can look at his description. To try to do it using a while loop, next to impossible. Using recursion, you can actually do it pretty elegantly. Okay? So the next question, we want you to understand how this is done in a computer. So how does the computer handle recursion? Okay? So let's take a look at a very simple example. Here he has the function a of 10. You can see his, function a. If I is 10, he calls a of 9. Otherwise, nothing happens. In effect, we return. Okay. So this is a very simple and not, actually, do I want to even go over that example? I'd rather go over this example. Yes, I like this example better. So we'll go over this example. So this example is going to say while I is greater than 0, we're going to call a of I minus 1. So the base case is I equals 0. If I is equal to 0, we're returning. We're not doing anything. It's a void function. Whatever we do, we're doing in the recursive function. And you can see what he's doing in the recursive function. He multiplies the argument I by 5. Then he prints out the argument and the product. Then, if I is greater than 0, he recursively calls a with I minus 1. So he's doing all the right things. He's breaking the task into a smaller task. So with recursion, I said one or more smaller tasks. So in this case, it's just one smaller task. And then he is, after he comes back from his recursive call, again printing out what I and j is. And then he's going to trace this function with setting I to equal 16 in main, and then calling a with 3. Okay, so let's see what happens. So remember we said that functions have stacked frames. So main starts out with a stack frame, and when we call the recursive function, it remembers that the call was made at line 16, and that at that point in main, the value of I was equal to 16, because he set I to 16. That's the one local variable in main. And the top of the stack currently points to main. Now we are into A3. So in fact, when we call, we have a stack frame for main. This is main. And in it, I is 16. And we're also keeping track of, we return to line 16. It's just coincidental that I is 16 and we return to line 16. Now, when we call ace of 3, a frame gets added for ace of 3. It has I equal to what? 15? Not 15. We're calling A with an argument of 3. I heard it. So right there is I, so I is set to 3. It's a different copy the two i's are independent. That's what Dr. Planck is trying to show you. The two i's aren't the same i's. They're different i's. And now j gets set to 15. So when we print on line 6, it will print I equals 3. Our output will print I equals 3, j equals 15. And it actually says in procedure A, but we'll just, for the time being, I equals 3, j equals 15. Now we get to line 7. I is 3, it's greater than 0, so we call A of 2. And we're going to remember that we are at line 7. So here, actually, maybe I should just put it out. We're at line 16. When we come back, we're going to be at line 7. With A of 2, I is now equal to, in this new stack frame, 2. And j will get set to 10. So the point is, the way the computer is handling recursion, it's allocating a new stack frame for each recursive call. And that new stack frame can hold different values for the same variables. So the stack frame for A sub 3 has I set to 3 and j to 15. For A sub 2, it has I set to 2 and j to 10. So again, in A sub 2, we now print out I equal 2, j equals 10 on line 6. We go to line 7, and we're going to call A sub 1. And again, we remember that we're at line 7 when we return. Here, I is equal to 1. J gets set to 5. We print out I equals 1 and j equals 5. And we call, do we call anything? Is I greater than 0? Yes, so we're going to call A sub 0. So we're at line 7. I is 0. J is 0. Okay. We print I equals 0. J equals 0. Now, in A sub 0, do we call A sub minus 1? No, because now I is equal to 0. So the recursion stops here. So we immediately drop down to line 8, and we again, notice he said later in procedure, so we print I equals 0, j equals 0. And now we return from the function. And at that point, we pop the stack frame for A sub 0. And notice we remembered which line we come back at, line 7. So we come back and we are at line 7 in A sub 1. So now we drop down to line 8, and in A sub 1, we print out its value of I, which is 1, and j is equal to 5. So we're in A sub 1 at line 8. We now exit the function. So we pop A sub 1 off. It's gone. We return to the top stack frame, which is A sub 2. It's said to return at line 7. So we are going to come in at line 7. So the next line is line 8. And that's a print statement. We print I equals 2 because I is equal to 2 now, and j is equal to 10. We exit because line 9 is an exit. Okay, so now we're back to A sub 3. Again, it says we're at line 7. Very good. We drop down to line 8. We print out I equals 3, j equals 15. And we exit, popping the frame. And now we're down to main. And the last thing we do in main, so we return at line 16, drop down to line 17, and that's a print. We print out main and the value of I, which is what? 16. So that's our output, except I didn't put the in procedures and later in procedure. But do you see how the computer's handling recursion? Every time a recursive function is called, it simply stores or allocates a new stack frame, adds the stack frame to the top of the stack, initializes the new stack frame, initializes the local variables, sets the parameters to whatever the arguments are, and it remembers which line it was executing in the function. Now it does that actually for any function call. Whether it's recursive or not, it always remembers at what line it was executing when the function was called so that when we return, we can pick up execution from that line. But hopefully you see how recursion can get implemented and we can have multiple recursive calls and the computer never gets confused about what's happening. Okay, in effect, its subtasks are just, some subtasks are waiting to be perhaps performed, and you keep executing new subtasks. So these are waiting. So that's what happens until the smaller subtasks get completed. Yes?
If I want to use, like, in each pass of the, I guess while you're doing each subtask, is there a way to use, like, a variable that was in a different?
No.
Okay. I can use, like, pointers or something to get around it, or do I have to pass it in?
You could pass it in as a pointer. There's tricky ways to do it that you shouldn't try.
Okay.
Okay?
Got it.
So yes, clever hackers could get access. You could pass a pointer in, and that way you could only use the same variable once, but it's nasty. Okay? Generally, the only variable, outside variables you can get access to in any function is a global variable, which we strongly discourage you ever from using. Okay, so generally, a function can only look at its variables plus globals. Now, I guess the other exception is reference parameters. When you pass a reference parameter, you're actually modifying a variable in the calling function. Okay, so in fact, quicksort, the quicksort algorithm that I showed you, you would actually pass the vector in quicksort by reference because you're doing an in-place modification. So every recursive call to quicksort is actually modifying the vector that would be in main. Okay, so let's do the same. Now you may wonder, okay, that was one recursive call. What happens with, let's look at now the Fibonacci one, okay, just for grins. So our Fibonacci was fib of n minus 1 plus fib of n minus 2. Okay, so let's take a look at what happens if from main we were to call fib of 4, a very simple one. Okay, so our Fibonacci function, let's just write it out. I'm going to write it with pseudocode. Essentially is if n is equal to 0 or n equals 1. Remember, this is pseudocode. Return n, or actually we can just say return, that we don't return n, we return 1. Else we return fib n minus 1 plus fib of n minus 2. Okay, so let's see what the stack looks like in this case. So we start with main, and it's calling fib of 4, so we don't really care what's in main. So we call fib of 4, and n is equal to 4. So the first thing fib of 4 does, it checks to see if n is 0 or 1. It's not, so it calls fib of 3. So you can see fib of 3 gets pushed on, and it has n equals 3. Okay? Fib of 3 immediately calls what? It calls fib of 2. So when we have fib of 3, n is not 0 or 1, so it comes down to the return statement. Fib of 3 calls fib of 2. So you can see that there's only actually 1/2 of the calls on the stack at any one time. So now fib of 2 is going to call fib of 1. So fib of 2, n is not 0 or 1, so we come down again to the return statement. Fib of 2 calls fib of 1. What does fib of 1 do? It returns 1. So this comes off the stack, and in effect, we are now halfway through our function. We now have 1 plus, what's the next thing that fib of 2 calls? Nope, it already called fib of 1. It calls fib of 0. And with n equals 0, what happens? It returns 1. Off comes the stack frame. So it's 1 plus 1. So we return 2 from fib of 2. So now we boot it off the top, the stack, and we return to fib of 3. So the first call is done. We've finished the call to fib of 2. And now what does fib of 3 call next? Fib of 1. So it calls fib of 1 with n equals 1. It returns 1. So we have 2 plus 1 is 3. It returns 3 to down here. Hopefully you see what is happening. Okay, so effectively, it's just deferring its work. So it's doing 1/2 of the problem first, doing all that work while it says, okay, I'll wait on the second half. Then when it finishes the first half of the problem, this is the first half. Okay, that's the first half. When it gets done with the first half, it goes to work on the second half. So the stack kind of keeps track of everything. When I said that recursion is another version of flow of control, what's kind of controlling everything is the stack. The stack keeps track of where we are in our computation. And the reason that recursion can take up a lot of memory is because if you have a lot of recursive calls waiting, you have a lot of stack frames. So potentially, if you're not careful, and notice with Fibonacci numbers, the stack never actually grew that big. The biggest the stack ever is going to grow with Fibonacci based on what we did is up to n frames. But it's going to take an exponential amount of time because it's like an accordion, up, down, up, down, up, down, up, down, a whole lot of times. Okay. So one thing you have to be careful about, recursion does require more memory because it's taking stack frames. And it also, if you're not careful, can require a lot of recursive subcalls. But if it's used properly, it can be a very powerful tool. Okay? So, questions about that? Okay, I'm going to let you think of one prompt. Give you a couple minutes. In fact, you do this on one of the exam questions. So a palindrome. How many have heard of palindromes? Some, but not all of you. Okay, so a palindrome is something that looks the same both forward and back. So for example, 580085 is a palindrome because if you read it forward, it's the same as reading it back. ABBA is a palindrome. It's the same reading forward and reading back. Remember the first top coder problem we ever looked at? We were trying to compute palindromes. Okay? So my question is, if you're given a string, remember you can think of a string as a vector, you want to write a recursive definition of whether that string is a palindrome. So I give you a string, so it's bool, and the question, is it a palindrome? I'll call it word. So you should return true if it's a palindrome and false otherwise. Okay, so the question is, can you write a recursive definition for this? I don't expect you to write the function just now, although if that's easier for you, you can write the function. But try to figure out if you can write this thing as a recursive definition. Give you about 3 or 4 minutes, and you can work with a friend on it. Remember, a string can be treated as a vector. Actually, I'll give you something else. You kind of need I'm going to give you int low and int high, which is a big hint about what you should be doing. So you're trying to determine whether this word is a palindrome from the low part to the high part. You kind of need low and high. Yeah, it makes it easier. Okay. Got a couple minutes, so I'm going to show you the solution. So for it to be a palindrome, the first and last letter must match, right? So the recursive case is kind of that the first, okay, if the first and last letter don't match, it's false, right? So if first and last letter don't match, we return false. Else, we're going to return, it's the subcase, we'll return the result of matching, return is palindrome on the string word with low +1 and high -1, because we're going to chop off, in effect, the first and last letter, right? So if the first and last letters match, what we want to consider next is the remaining part of the word with the first and last letters chopped off. So that's low +1 and high -1, right? So that's the recursive case. Now, we need a place to stop. Okay, what's one obvious stopping point? The middle element. If it's one element. So one obvious thing should be if low equals high. So the base case, okay, if low is equal to high, what do we return? True, because a single element is always a palindrome. A one-word element is by definition a palindrome. Now, the other base case is a little trickier. Okay, what if we have an even number like here? Okay, eventually we get down to 0, 0, and the question is, should a two-letter word be a base case? Okay, the answer can be yes or no. I see you nodding, no worries. The question is, do we define an empty string as a palindrome? Okay, I would say it's probably easier to just define the empty string as a palindrome. If you decided that a string of length 2 is the base case, that's fine too. Okay, so my other case would be else if low is greater than high, it means that we also return true because we have an empty string. So this case right here is the empty string. If low is greater than high, we have an empty string. Okay, but if you stopped your recursion at a word with 2 characters, I'm fine with that too. Okay, generally it's a little easier to go to in effect 0, and the empty string is 0. Okay, so that would be your 2 base cases for a palindrome is a string of length 1 or a string of length 0. Otherwise, you compare the first and last characters. If they match, you compare the smaller string with the first and last characters lopped off. Okay, I will see you all on Thursday where we'll go over Sudoku, a big example of recursion. Also, Thursday gives you a good idea of how to do Lab 9. So that's another thing.